So far, we have been talking about caching data, but keep in mind that when you execute a program, you need to bring in both instructions of that program as well as its data. So where do you store instructions? Like data, you store instructions in memory as well, and those instructions are also stored as part of data in the program's address space. So when you access instructions, so when you execute any instruction, you need to access memory to get its instruction machine code. And so for every instruction, you have to access the memory system. Obviously, accessing main memory for every instruction would be expensive. So just like data, we would like to cache instruction as well. And so for all cache design problems, you can pretty much assume that instructions are treated in the same way that data is treated in terms of how you store them in the cache, what kind of a replacement policy makes sense, and the direct mapped cache that we talked about may also make sense. Now, the only time when it actually makes a difference or a distinction is for the L1 processor cache. So when we designed the memory hierarchy, we said we have a cache at the top of the hierarchy, and then we have the main memory, and then we have the disk. So in the previous lecture, we said, well, in reality, cache is not just one structure, but it is actually composed of several levels. So you have level 1, level 2, level 3. Level 1 is the smallest one, level 2 is slightly bigger, level 3 is even bigger. And the reason why we use so many levels is to bridge the space and latency gap that exists between a small L1 cache, which is of size 32 kilobytes or so, with main memory, which is several gigabytes, and it takes hundreds of cycles to access. L1, on the other hand, just takes one cycle to access. Now, L2 and L3 stores instructions in the same way that you would store data. So there's not much difference. But for L1, in some processors, they choose to have two L1s. One for the data cache, like we have been talking about, and one for the instruction cache. So now what are the advantages of having two L1s, one for instruction cache and one for data cache? Well, L1 is a level 1 cache, and it happens to be very sensitive to latency. So we want to be able to access these L1 caches really fast at the clock cycle of the processor. So one cycle, which is 1 nanoseconds. So we can't really afford these caches to be too big. So we can use either one cache, let's say a 32 kilobyte cache, and store both instruction and data in it. So in that case, instruction and data are going to be competing for space with each other. Alternatively, we could say, well, let's have two caches, two L1 caches. One stores data cache and one stores instructions. Now, the advantage of this is when I have a instruction fetch, I know exactly which of these two caches to access, because instructions are going to be stored in the instruction cache, so you just need to access instruction cache. So even though in aggregate I have two caches and the total size is twice that of what I would have otherwise had, the two structures are isolated, so the time it takes for me to access an instruction cache is only proportional to the size of the instruction cache. So the latency doesn't increase. Of course, the area doubles, but the latency of accessing instruction cache does not increase, which is super critical for this level 1 cache. So the main advantage of having these two caches is that the instruction fetch would access instruction cache at a very fast time, and then a load or a store instruction in the memory stage of the pipeline would access the data cache, and again they can operate very fast. So if you look at the pipeline diagram, now we can replace the structures with our instruction cache and data cache, right? So now these are a little bit more realistic representation of what an actual processor looks like. And instruction cache and data cache, which are level 1 caches, they operate at the speed of the processor clock cycle. So if you assume that the processor clock cycle is 1 gigahertz, they can operate at 1 nanoseconds, and so you would not observe any extra stall than what we had already assumed in our pipeline design. However, we can have cache misses, both in instruction cache and data cache. And when you encounter those cache misses, you're obviously going to be stalled for the time it's going to take to access the next level of the memory hierarchy. So if it is the next level is level 2 cache, it may take maybe 10 cycles to get there. But if the next level is main memory, it's going to take 100 cycles to get there. So it's going to take a long time for these cache misses to be serviced. Modern processors have ways and mechanisms to somehow do useful work when you are waiting for this data to come back. So there are ideas like out-of-order processors and prefetching, etc., that are being employed to solve that problem. We won't go into the details of those ideas, but if you take 470, you can dig a bit more deeper into those challenges and ideas. All right, to summarize, we talked about direct mapped caches today. The main idea to take away is that if I have the freedom to store a cache block in any cache line, then I need to do a lot of tag comparisons, as many tag comparisons as there are number of cache lines. So in this example, I have 4. So the main idea was I wanted to restrict the number of places that a cache line can be stored in. So we went and said there is going to be exactly 1 cache line where you can store a cache block. And so the way you would figure out which cache line it's going to be is by using a few lower order bits in your address, and the remaining bits in that address would be the tag. So in the next lecture, we're going to be talking about what's called as a set associative cache. Now I'll briefly introduce set associative caches today, and then I will go into a bit more depth in the next lecture. So the downside of the direct mapped cache is something that we identified when we talked about conflict misses. So the problem is it is too restrictive. So when we talked about fully associative cache, it is too permissive in terms of where you can store the data. And direct mapped cache goes to the other extreme and says, well, there is exactly 1 cache line where you can store the data. And that can lead to performance loss, because if the program happens to access the cache blocks that are mapped to the same cache line, then only one of them can be stored. So you have this thrashing effect where one block would kick the other block repeatedly, and then you don't really use the cache productively to cache anything, right? So we had talked about this pathological ABA pattern where A and B are mapping to the same cache block in a direct mapped cache, and they keep kicking each other out, and then you end up with all misses. So we want to give a little bit more freedom than just saying, okay, 1 cache line is where you can go to. How about 2 cache lines? And how do we architect that? Well, that takes us to set associative caches. So now I have 2 cache lines that are colored in the same way. So I'm going to call that as a set. So I have a cache line 1, cache line 2. Both are grouped together in the form of a set. And I have another set with exactly the same geometry. So before I was using index to select one of the different cache lines. Now I would use this index to select one of the cache sets, where each set is going to be a set of cache lines. Now, why is this better? Because now if a cache block maps into a set, right? Because the set index is only going to select the set, but it doesn't select which cache line within that set. So that gives us a more freedom, because now I can choose to store my cache block in any one of the cache lines within that set. I'm going to call the cache lines within the set as ways. That's just a technical term for referring to the different cache lines within a set. So I can choose whichever way I want to store in. How do I select which one? Well, we're going to bring back our ideas from temporal locality, where for a fully associative cache, we use this heuristic LRU, least recently used policy. Now, instead of applying the LRU policy for across all the cache lines like we did in the fully associative cache, now we are going to apply it only within a set, between the cache lines within that set. So we have these cache blocks that map to this set. So I'm just mapping to the set, not necessarily the way. So I have 4 cache blocks that map into this set, and so I can now choose one of the 2 cache lines that is available for storing it, and when both of them are full, I would pick the cache line which is least recently used among those 2.